In this circuit, we have a 12-volt battery, a 2 farad capacitor, which we're assuming is starting off empty, and a 3 ohm resistor. And in that situation, if we just connect this and let it go, what would you expect to happen here? What's the first thing that's going to begin happening?
Current will flow from the positive end of the battery to the negative end.
Yeah, we should expect current to flow. And yeah, let me go ahead and mark the positive terminal and the negative terminal. Generally, if they're not marked, you can assume the longer bar is positive and the shorter bar is negative. So yeah, we're going to get current flowing from that high voltage region caused by the positive terminal of the battery towards the low voltage region. And since there's just one path, we can assume that the current is the same everywhere in that path. Everything's in series, there's just one single loop. However, that current's going to change as time passes, because as soon as current starts flowing, what's going to happen to the capacitor?
It's going to start charging.
Yeah, the capacitor starts charging. The plate most directly connected to the positive terminal of the battery starts gaining positive charge as electrons flow out of it. And the plate most closely connected to the negative terminal of the battery starts accumulating the same amount of negative charge as extra electrons accumulate there.
Is that always true for if there's one battery and one capacitor, that like the negative sides will be closer to each other and the positive sides?
Yeah, and ultimately the reason for that is the capacitor has its own delta voltage, and for a capacitor, the positively charged plate is always higher voltage and the negatively charged plate is always lower voltage. So the plate that's connected to the high voltage region is going to get positive charge. The plate that's connected to the low voltage region is going to get negative charge.
Okay.
And you can also kind of see that from the mapping out the voltages approach we were looking at earlier with circuits with just lots of resistors. This region is going to be high voltage because it's connected to the positive terminal of the battery. This region is going to be low voltage, and there's of course a voltage difference here, but eventually you're going to have this region be low voltage also. Because as charge accumulates, that means the capacitor now has its own voltage difference. What does that tell you about the resistor? If the capacitor is now getting some delta V.
But it also has to have a delta V, and those two have to equal the EMF of the battery?
Yeah, because the battery is providing a boost in voltage. Both the capacitor and the resistor can sort of use up some of that voltage. They both involve a decrease in voltage, because if you go from positive plate to the negative plate, you're going from high voltage to low voltage. So the battery provides plus 12 volts. You lose some of that voltage through the capacitor and the rest of that voltage through the resistor. So if the capacitor is getting more charge, it involves more of a voltage drop. So there's less voltage available for the resistor, and less voltage on the resistor does what? What happens if you have less voltage for the resistor now? What is voltage for the resistor proportional to?
The flow?
Yeah, the flow of current. So if you have more charge on the capacitor, that means more voltage is needed by the capacitor, which means there's less voltage available for the resistor, and that means current slows down. So as the capacitor charges up, the current gets slower and slower. But also the current is the derivative of charge. Current tells you how fast charge is accumulating on the capacitor. So slower current means charge is accumulating more slowly, which influences the rate at which current is changing. And so charge and current are both influencing each other in this sort of repeated feedback loop.
So when a capacitor is charging, it acts like a resistor?
I wouldn't say it acts like a resistor, because acts like a resistor doesn't just mean it has a voltage decrease. Acts like a resistor means something very specific. The most important characteristic of a resistor is its voltage drop, which is what formula?
Negative IR.
Right. So I would say that acts like a resistor means the delta voltage is proportional to the current. That's not true for a capacitor, though. For a capacitor, delta voltage is, what's the usual formula for delta voltage of a capacitor?
Q over C.
Yeah. And usually we're going to use negative Q over C just because of the directionality. Like if you're talking about in this direction, we are going from the positive plate, the high voltage zone, through to the negative plate, the low voltage zone. So that is a decrease in voltage. So in this direction, I would say that delta V is negative Q over C.
Okay.
And note that this does not act like a resistor, because a resistor, acting like a resistor means voltage difference is proportional to current. But a capacitor has voltage difference proportional to charge stored, not proportional to current. And likewise, I wouldn't really say a capacitor acts like a battery either, because the important thing about a battery is what is the delta V for a battery?
Just the EMF.
Yeah. In other words, a constant. That plus epsilon, whatever that happens to be.
Mm-hmm.
So sometimes people talk about a charging capacitor as acting like a resistor. Sometimes people talking about a discharging capacitor as acting like a battery. And I think what they mean by that is the capacitor is pushing back against the battery versus a discharging capacitor is pushing, I guess you might say, forward to make current flow. But
Okay.
I think it's very inaccurate and misleading to call that acting like a battery or acting like a resistor. Because acting like a resistor means delta voltage is proportional to current. Acting like a battery means a constant delta voltage. And a capacitor doesn't do either of those things. Capacitor has delta voltage proportional to amount of charge it stores right now. Any other questions on that so far? And moreover, we can use these formulas to write out the loop rule equation, which I think is going to make a lot more sense of the math behind this. If we write out the loop rule, we've got a battery, a capacitor, and a resistor. So what do we know about the delta voltages for the three of those things?
They add up to 0.
Yeah. These delta V terms all have to add up to 0. If we fill in these formulas, we get plus epsilon plus negative Q over C for the capacitor, plus negative IR for the resistor. Adds up to 0. And I think it's very useful in this case to add these negative terms to both sides. So we get IR plus Q over C equals the constant epsilon of the battery. In other words, the resistor and the capacitor can each get an amount of voltage, but they have to share the voltage of the battery because they're in series with each other. So
is that also true when discharging? Is that also true for discharging?
Yes, you can use this same model for a capacitor that's discharging. Typically, you would have a capacitor that's already charged, and there would be no battery. If there's no battery, you can use the same equation. It's just that epsilon will be 0.
Okay.
So in that case, instead of these two values adding up to some positive constant, you would have these two values have to add up to 0. So if it's discharging, in other words, no battery, you'd have IR plus Q over C equals 0. In other words, IR and Q over C are exact opposites. So in the charging situation with the battery, IR plus Q over C, the voltage that the resistor gets plus the voltage the capacitor gets have to add up to the voltage of the battery, which is a constant. Whereas if it's discharging, then they have to add up to 0, which means that the voltage the resistor gets is just the voltage the capacitor provides, but in the opposite direction. And that negative, as usual, essentially refers to direction of the current flow. This is going to mean that the current is flowing to decrease the charge of the capacitor, whereas here, current is going to be flowing in a direction to increase the charge of the capacitor.
What's the difference? Yeah, I was just going to ask, I don't really understand the concept of charge. Like when we're saying it's decreasing or increasing as compared to flow, if we were to graph them, you know? Yeah,
well, charge itself is just a mysterious property that certain particles have that makes them attract and repel each other. So that's kind of a strange way to say it, but really we don't know what charge is. It's just this property that some particles have and other particles don't, that we use to mathematically explain the idea of some particles attract or repel each other. But the charge, whatever it happens to be, is what's flowing when we talk about current in wires. And of course, what's actually going on is electrons are jumping from atom to atom. But we don't really care how many electrons or what volume of electrons or anything like that. We just care about how much charge is carried by the electrons as they move. So the charge on a capacitor, usually written as Q, that represents how much charge, sort of essentially a measure of how many extra electrons or how many deficient electrons is on these plates. Like a negatively charged plate just means this plate has too many electrons. Positively charged plate means this plate has not enough electrons to match the protons it has. So Q represents a measure of how much deficiency or gain of electrons there is. Not in terms of number of electrons, but in terms of the charge carried by those electrons. And we can say that current is the derivative of charge in the sense that the rate at which current is flowing tells you how fast the capacitor is gaining or losing charge on its plates. So this is really the key relationship between those quantities. Sometimes we say I equals negative dq over dt if we want to emphasize that the capacitor is losing charge. But in general, current is at least plus or minus dq over dt. Any other questions on how those are related so far? So let's see if we can investigate how current is going to be changing as time passes. Because we can expect that at the beginning there's going to be really fast current because the capacitor is not really pushing back yet. In fact, at the beginning, if there's no charge, this term is gone. So you just have IR equals epsilon. Whereas as time passes, Q is going to increase. You get more and more charge on the capacitor, which means more and more pushback against the current, and current is going to slow down. In fact, after a long time, what would you expect current to be?
0.
Yeah, eventually we get to a point where there's no current flowing at all because the capacitor eventually fills up so much charge on it that it's pushing back with the same amount of voltage that the battery is pushing forward with. If these balance out, the pushback from the capacitor and the push forward from the battery, if those balance each other out, there's no voltage left for the resistor, so no current is going to flow. And in cases like this, if you're expecting it to be exponential decay anyway, then usually the best thing to start with is to look at what's going on at the beginning, time 0, and what's going on after a long time. That would at least tell you a starting point and an asymptote. If you know a starting point and an asymptote, you can get a pretty good sketch of the exponential decay curve, even without any other information. So let's try that out. We'll look at the beginning and after a long time and try graphing that out. To start with, let's say we're talking about current. So if we're talking about time 0, at the very beginning, how much charge is there on the capacitor at the very beginning?
0.
Right. At time 0, there's no charge. The capacitor is uncharged, in this situation anyway. So if we fill that into the loop rule, we're going to get IR plus nothing equals epsilon. So if you solve for I, what do you get?
E over R.
Yeah. Which is exactly what we would get if we had a loop with just a battery and a resistor and no capacitor at all. So one way to interpret this is that a capacitor that's empty doesn't provide any voltage drop at all, which means it acts like what? What's a circuit element that doesn't provide any voltage drop?
A wire?
Yeah, wire. We can say that at this instant, not as time passes, but at this instant, you can kind of say the capacitor acts like just wire in the sense that it doesn't provide any delta V. So an empty capacitor at that instant acts like just wire. And of course, that's going to start changing as soon as the capacitor starts charging up. It's no longer true as soon as there's any charge on the capacitor. But if you're just looking at what's going on at this one instant in time, you can treat an empty capacitor as just wire and analyze the simplified circuit without the capacitor at all. That at least tells you how much current you get. And we have values for epsilon and R. So let's fill those in. 12 volts and 3 ohms gives us 4 amps. So that's the initial current, which we might call I sub 0 because it's the current at time 0, or sometimes called I max because it's the maximum current we're going to see in this system. All the other currents are going to be weaker than that. So we know what's going on at time 0. That gives us a starting point for our graph of current. And we also want to know what's the asymptote, what's going on after a long time. So after a long time, what do we know about this equation, or what values do we know after a long time? What would we expect to happen?
Current goes to 0.
Yeah, eventually current is going to be 0. Or at least current approaches 0. Mathematically, it never gets there because it's an asymptote, but we can assume it gets close enough to 0 that it may as well be 0. The capacitor is eventually going to stop current entirely. It blocks the circuit, which means that acts like what? What would be something that could happen in a circuit that makes it so no current can flow at all?
Like a switch?
Yeah, if you have a switch that's turned to the off position, an open switch. So in fact, you could kind of think of a capacitor, if it's full or empty, as a switch in those two positions. An empty capacitor acts like a switch that's closed and allows current to flow without any pushback at all. A completely full capacitor acts like an open switch. It doesn't allow any current to flow at all. And of course, in between those times, it changes drastically. It doesn't really act like either one. It's providing an amount of pushback proportional to the charge. But at those two instances, completely empty and as full as it's going to get, it behaves in a very predictable, simplified manner. So after a long time, we've got no current, and we can actually rewrite the loop rule in those circumstances also. If we fill in 0 for current, we get Q over C equals epsilon. In other words, the capacitor is getting all the push from the battery. And that means we can now solve for Q. Multiply both sides by capacitance. So the amount of charge stored is going to be the epsilon of the battery times the capacitance of the capacitor. That also means that full doesn't just depend on the capacitor. Full means a property of both the capacitor and the battery it's attached to. If we fill this capacitor up, that doesn't mean it can't store any more charge. It just means it won't store any more charge under these circumstances. But if you take that full capacitor, unplug it, and plug it into a stronger battery, it will continue accumulating more charge until it is full relative to that new battery. So when we say a capacitor is full, that's a description of the capacitor and the situation it's in, not just a maximum charge that capacitor could ever hold. In this case, that's going to be capacitance times voltage, so that's 2 times 12, 24. And farads is actually coulombs per volt. So when we multiply coulombs per volt times volts, the volts are going to cancel out, so we just get coulombs. So 24 coulombs is the charge that's going to be stored by the time this capacitor is as full as it's going to get. So we would call that Q max. Any questions on that so far? So we can now say that the current starts at 4 amps and decays towards 0 as an asymptote. And meanwhile, the charge in the capacitor starts at 0 and decays upwards towards 24 coulombs as an asymptote. And we should now be able to graph both of those. So if we set up a graph of that, let me just make a note of our starting and ending values. Q initial is going to be, what was that, 0. Q final, Q max, is going to be 24 coulombs. And then as for the current started off at 4 amps. And the final current, after a long time, is going to be approaching 0 amps. So we know those are going to be the important values to look for on the y-axis, the current or charge axis. So to graph those and maybe make some equations of them. Let's say, and of course, we're going to want to graph these on two separate graphs because charge and current are keeping track of two different things. So let's make a graph of time versus charge on the capacitor and another graph of time versus current in the resistor, which is really just current in the entire loop because it's just one path anyway. And we know that the important values we want to keep track of for charge are 24 coulombs and 0 coulombs. And for current, 4 amps and 0 amps. And to graph these, we know that charge starts at 0 and approaches an asymptote of 24. So even without doing any further calculations, we can draw a sketch of the exponential decay graph we would expect. That we expect it to start at 0 and decay upwards towards an asymptote of 24 coulombs. And likewise for the current graph, we know it's going to start at 4 amps as the initial value and decay downwards towards a final asymptote of 0 amps. So we can expect that graph to look something like this. So we've got sketches of the graphs without any further information. Any questions on that so far? And how could we add some more detail to these graphs? What other information could we provide that will make these graphs more useful, more accurate?
Like half-life or time constant?
Yeah, if we can get some information about how much time it takes, like you said, either the half-life or the time constant, then we can actually put some markings on here and maybe even label some specific data points. So let's try that. Because so far, we don't really know if it's approaching the asymptote like this, or like this, or like this, or like this, or like this. All of these would be valid graphs just based on what we know so far. If all we know is it starts at 0 and approaches 24, we don't have any information yet about how quickly or slowly it approaches the asymptote. But that's what half-life and or time constant is all about. So let's try that. Let's see if we can establish how much time it takes to decay a certain amount.
Why do we have?
Sorry, go ahead.
I was just going to say, why do we have time constant and half-life if they both just tell us about the rate of decay?
It's ultimately just two different ways of writing the rate of decay, depending on whether you, I mean, half-life, how do we define these in the first place? Like, what does half-life mean?
The time it takes for half the amount to decay to half of the initial value, or halfway between the initial and final.
Right, because if it's decaying towards 0, it's time to decay halfway towards 0. But if it's decaying towards some other asymptote, it's time to decay halfway towards that asymptote. So for instance, if you're going from 0 to 24, one half-life would take you from 0 to 12. And then another half-life would take you another halfway from 12 to what, 18 is halfway to 24? And then from 18 to 21, from 21 to 22 and a half. So each step goes halfway towards the asymptote. So halfway towards the asymptote. And then the time constant, usually written as tau. Let me mark this. This is usually written as capital T, or sometimes capital T sub 1/2. And that is just an amount of time. The time constant is related usually written as the Greek letter tau. It's exactly the same definition except for what slight change.
It's tau times ln2 is.
In terms of calculating it, yes, but what does that actually mean? It's the time it takes for what to happen?
2/3 decay?
Not 2/3, although it is fairly close to 2/3. Specifically, it is the time it takes to decay instead of 1/2 of the way, 1/e of the way towards the asymptote. So 1/2, that's 50%. 1/e ends up being about 37%, so a little more than a third. In other words, there would be about 2/3 of it gone and 1/3 of it still remaining, approximately. There's nothing special about 1 over e. It's just a convenient reference point because we use e as the base in the exponential function by default. But then again, there's nothing really special about 1 over 2 either. It's just a convenient reference point that makes the numbers work out easily. So these are just two different ways of describing the amount of time it takes for a certain significant quantity to decay. It's just a difference of, do we want to talk about amount of time it takes for half to be left or amount of time it takes for about 37% to be left. And in my experience, the usual result of this is if you're talking about half-life, the amount left tends to be easy fractions to deal with, but the amount of time tends to be an inconvenient irrational number. Whereas if you're talking about time constant, the amount of time tends to be nice, neat whole numbers or easy fractions, but the amount left tends to be irrational numbers because of the 1 over e.
So is it the time it takes to decay? So say it's like 1 over e is about 1/3. Is it the time it takes to decay 1/3 or decay to 1/3?
To decay to 1/3 of the amount left. So for instance, if you start at 4, after 1 time constant, you'd be about 1/3 of that. So about 4/3.
Okay, so it's decaying by about 2/3 then.
Yeah. Specifically more like 63%, but pretty close to 2/3. And you can also find that by just taking the original amount or the original difference and dividing by e. So you go from 4 to 4 divided by e, and then 1 more time constant, you'll divide by e again. So you'll get original amount divided by e squared, then original amount divided by e cubed, and so on. So that's the difference between what these mean. And let's try actually calculating those. Do you have a formula for what to expect the time constant or the half-life to be in a circuit like this?
Isn't time constant RC?
Yeah, if you just got a single loop with 1 resistor, 1 capacitor, and optionally 1 battery, then the time constant will always be resistance times capacitance.
If there's multiple resistors, would it just be R equivalent times C?
Yeah, if you've got multiple resistors, you can just, as long as you can combine them into 1 equivalent resistor that is in series with the capacitor, then that's fine. You would just use that total equivalent resistance.
Okay.
It's also possible to combine capacitors if they're in series or parallel with each other, like with other capacitors. It just follows the opposite rule from resistors. If you've got capacitors in parallel, capacitors in series, you would add the reciprocals of the capacitances to get the reciprocal of the equivalent capacitance. So these capacitors in series are going to act like a capacitor with smaller capacitance. Whereas if you've got capacitors in parallel, you would just add the capacitances directly.
Okay.
I don't think 7B is going to cover that. It usually doesn't. But if it comes up, capacitors add in a way that's exactly opposite to the way that resistors add.
Okay.
And you can treat many capacitors linked together as if it was just 1 big capacitor. So in general, if you've got a bunch of resistors networked together, you can combine them into 1 equivalent resistor. A bunch of capacitors networked together, link them into 1 equivalent capacitor. If you've got a mix of resistors and capacitors, it gets more complicated. But ideally, you want to be able to split it up into just resistors and just capacitors. And therefore, 1 equivalent resistance and 1 equivalent capacitance. And then the time constant is going to be R times C. For more complicated circuits, that won't necessarily be true, but as long as you can simplify it into 1 loop with 1 equivalent resistance and 1 equivalent capacitance, and optionally a battery, the time constant is going to be R times C. And that's true whether there's a battery or not. Charging or discharging will have the same time constant. And then half-life is going to be related to that. How would you convert the time constant to half-life?
Multiply by ln2.
Yeah, time constant is going to be, the half-life is going to be time constant times logarithm of 2. Because the time constant is in terms of E. To convert that to being in terms of 2 instead, you're going to need a multiplier of logarithm of 2. Any questions on that so far?
Do they both have units of seconds?
Yeah, because if, well, assuming you're multiplying, where was it? Ohms times farads. Ohms times farads turns out to equal seconds if you simplify the units of measurement. Now, if you had had like ohms times microfarads, you'd end up with microseconds instead. So keep track of metric prefixes if there are any. And all the metric prefixes you can just write as times 10 to a power. Like micro just means times 10 to the -6, or kilo just means times 10 to the third. But ohms times farads is always going to be seconds. So in this case, if we actually multiply these, 3 ohms times 2 farads will be 6 seconds. So the time constant in this situation is 6 seconds. Which means we could start labeling these graphs in terms of time constants to get more accuracy, more detail about how fast it decays. So let's try that. For instance, for the current graph, if I just put a mark every 6 seconds, let's say 6 seconds, and then same amount of time, 12 seconds, 6, 12, 18. So time in seconds. We can make markings here of how high or low it's going to be in terms of the current. Like if we go forward 1 time constant, we're going to be 1 over E of the original amount. So 4 amps divided by E is going to be 4 divided by E, about 1.47. Yeah, so about 1.5. So we can put a mark at 1.5. And of course, if you've got graph paper, you can make this much more precise. But let me just label these. We've got 1.47 amps of current at this time. And then 1 more time constant beyond that, 6 seconds beyond that. How would we find the current at this time?
6 divided by E, or 1.47 divided by E?
Yeah, the value is 6 seconds. So 1.47, divide that by E. Or you could also interpret that as 4 amps divided by E and divided by E again. So you could take the original 4 amps divided by E squared. Either way will get you the same thing. So 4 divided by E squared, I'm getting about 0.54. And note that this is approximately 1/3 of the original. 4 amps, 1/3 of that would be about 1.67, 1.33. We're dropping to a little more than 1/3 of it. 1/3 of this would be a little less than 0.5, but we're going to a little more than 0.5 instead. So you drop to a little more than 1/3 of the original. And then 1 more time constant, we take 4 divided by E cubed. So we're dividing by E, dividing by E, dividing by E. And it looks like about 0.2. So that gives us a much more accurate set of data points to use to drawing this curve. And if you want even more accuracy, more data points that are fairly easy to get, you can also use the half-life. So if we mark in the half-life is that same tau, 6 seconds, times logarithm of 2. So if we take 6 seconds times natural logarithm of 2, that's going to be about 4.16.
Mm-hmm.
So we could also mark those as times on the graph if we want even more accuracy. So 4.16, about here. And also 2 times the half-life would be 8.32. I guess that'll be closer to 6. And then 3 times the half-life would be 12.48. And then 4 times the half-life would be 16.64. So by marking these other data points, we can get more data points on the graph and more accuracy. And like I said, the time constant leads to nice, easy amounts of time, but irrational amounts of, in this case, current. The half-life leads to irrational amounts of time, but it's going to be easy values of current, because after one half-life, how much current is left?
2 amps.
Yeah, exactly. Half of 4 is 2. So that's 2 amps. And then one half-life later, half of that would be
1 amp.
So we're down to 1 amp. And note that these fit in nicely between the values we already got for time constants, because these are all still talking about the same decay process. We're just looking at it in different time intervals. Likewise, after another half-life, we decay to half of 1 amp, so that'll be 0.5. One more will be decaying one more halfway, so another half of 0.5 would be 0.25. And this gets us a lot of data points, making it much easier to draw in a remarkably smooth, accurate curve, linking all those data points together.
Are half-life and time constant relevant for charge also, or is it just in terms of current?
It's relevant for everything that's decaying. So in fact,
Okay.
everything in this current that's decaying, whether you're graphing current or charge stored on the capacitor right now, or the voltage on the resistor or the voltage on the capacitor, those are all going to decay with the same time constant and same half-life, because they're all decaying together.
So after 4, I was just saying, so for the charge one, after 4.16 seconds, there'll be 12 coulombs of charge.
Right, because it's going to decay halfway towards the asymptote. So if we try filling those in, and by the way, this is one reason why I like to graph, if we're graphing two things happening at the same period of time, graph them vertically stacked on top of each other like this, so that you can mark the same times on both axes. Like we know that these times are going to be important. 4.16, mark that on the same point on the axis. And 8.32 and 12.48 and 16.64. Let's extend that a little further. So yeah, each one of these intervals of time represents not half of the original amount, because half of 0 would still be 0, but instead going halfway towards the asymptote. And I think it's very useful to think of this in terms of what's decaying is not the value, but how far it is from the asymptote. To begin with, we are how far from the asymptote?
24 units.
Yeah, we're 24 units, 24 coulombs below the asymptote. One half-life later, we'll take half that difference and we'll be 12 below the asymptote instead. So 12 below the asymptote is now 12. And now we'll take half of that 12 below the asymptote. Half of 12 below would be 6 below. So that'll be at 18. Now we're 6 below, so we decay to half of that. 3 below would be 21. And then half of 3 below would be 1.5 below. So we're now at 22.5. Make that a little more horizontal. So that gets us a list of data points at all of the half-life, in the convenient half-life instants in time. And again, note that these are kind of inconvenient times because they're these irrational numbers. But the amounts of charge are very nice, neat, easy to work with numbers, because we're just going halfway, 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 halfway.
So for discharging, that would the calculations be the exact same? So we'd have the same relevant time points? The
difference would be that, yeah, it would still have the same time constant, same half-life, because that was determined only by the values of resistance and capacitance. That's going to be true whether there's a battery there or not.
Okay.
So if you're still talking about the same capacitor that we've been using and the same resistor that we've been using, the time constant and the half-life will be the same values whether it's charging or discharging. The battery or lack of battery is just making a difference of whether you're starting low and increasing or decaying upwards towards a positive asymptote, or starting high and decaying downwards towards 0 as an asymptote. Or alternatively, if the capacitor, we know the capacitor in this circumstance can hold 24 coulombs. But if we started with the capacitor with more charge than that, maybe it already had some charge from a stronger battery in another circuit. If the capacitor started off with more than 24 coulombs, what would you expect to happen? If you've got too much charge in the capacitor.
Would the time constant in the half-life be longer, or is?
Those are determined only by the resistance and capacitance, though, so those are still the same. But yeah, it's going to go down to 24, because if the 24 coulombs is the equilibrium situation, it's the situation where the capacitor and battery balance out exactly. But if the capacitor has more than 24 coulombs, that means it's pushing back stronger than the battery's pushing forwards. The capacitor has too much voltage. So that's actually going to make current flow the opposite direction. If the capacitor starts with too much charge, current's going to flow backwards against the battery, if this is a battery that even allows that to happen. And the capacitor is going to discharge until it reaches 24 coulombs. So we get exponential decay from above towards 24 coulombs. Or if it starts with anywhere less than 24 coulombs, even if it started off like partially charged, it's going to exponentially decay upwards towards 24 coulombs. But regardless of how much charge it starts with, in this circumstances, it's going to decay towards 24 coulombs, whether that's from above or below, because that's the equilibrium value. Also in this, sorry, go ahead.
I was just saying, if we have time real quick, can we just do the voltage graphs too for the charging?
Yeah, let's try the voltage graph
shape
as well, because I think it's I mean, we of course we could fill in 6, 12, 18 on this one with the same sort of values. We take 24 below and divide that by E, then take that distance below, divide by E again. So again, it's the difference that we're dividing by E each time. But that just gives us this more points on this smooth exponential decay curve. But yeah, let's try graphing out voltages as well. Because the voltages, one of the nice things about voltage is that we can put both voltages on the same graph. It's not really a good idea to put charge and current on the same graph because the y-axes are measuring different things. But if we look at the voltage of the capacitor and the voltage of the resistor and even the voltage of the battery, those are all measuring the same thing. They're all measured in volts. So we can put them all on one axis. And I'm going to write this as absolute value of delta voltage, because formally the battery would be providing positive 12 volts, and the current and the capacitor and the resistor would be providing negative values for delta voltage. But I think it's going to be easier to see what's going on if we look at these as absolute values. We know the battery's got 12 volts, and that just stays there forever. So we can graph the battery as just a constant 12 volts. Battery starts with 12 volts and continues there forever. Whereas the capacitor, how much voltage does the capacitor start with?
Zero?
Yeah, at the very beginning, the capacitor has 0 volts. And what about the final voltage? If the capacitor eventually has 24 coulombs of charge, how would you convert that into a voltage?
24 divided by the capacitance.
Yeah, because as always, we can go back to the idea that delta voltage of the capacitor, at least as an absolute value, is charge over capacitance. So the final charge, 24 coulombs, divided by the capacitance, 2 farads, 24 over 2 would be 12 volts. So the capacitor is going to exponentially decay towards a final voltage of, or towards an asymptote of 12 volts. And we could also put in the time constant or half-life marked on the time axis to plot some data points, but I'm just going to sketch this in for now because we're low on time. So the capacitor's delta voltage graph is going to look something like this. That the capacitor starts with no voltage because it's empty, no charge. And as it accumulates charge, it gets more and more delta voltage. Whereas the current starts off at 4 amps. How do we convert that to a voltage? delta V for any resistor is going to be what?
IR, negative IR.
Yeah. And let's look at it as an absolute value. So just IR. So we start with 4 amps times 3 ohms is 12 volts. So the resistor's voltage starts at 12 volts and eventually decays towards what?
0.
Yeah, it's going to have 0 as an asymptote because eventually it has 0 current times any resistance will be 0 volts. So that's going to be decaying, exponential decay downwards towards the asymptote of 0. So we can put all these on the same graph because they're all measuring the voltage as time passes. And at any single instant in time, like let's say we look at this cross section. At this instant in time, we've got a delta V for the resistor and a delta V for the capacitor. What do those have to add up to?
12.
Yeah, those have to add up to 12 volts. So this graph, I think, makes it a lot more visually easy to see that as one of them gains voltage, the other one has to lose voltage because they've got to add up to the same constant voltage provided by the battery.
Okay, but technically, if we graphed it without absolute value, this would all be below the x-axis, like it's going to negative
and resistor
12.
would be below the axis. The battery would still be at positive 12. Yeah.
Okay, and they would be adding up to negative 12.
Yeah, or to put it another way, all 3 of them, the negative value for resistance plus the negative value for capacitor plus the positive value for the battery would all add up to 0. So it's really just a visual way of representing the loop rule equation and how it changes as time passes.
Okay, thank you.
You're welcome. See you next time.